Thank you. So session 6 is about grid forming and other inverter-based resource activities, developments, plans. And the session will be chaired by Julia Matevosyan. I think everybody knows Julia. I don't really need to introduce her. So I'm just going to turn the session over to Julia. She's got a great lineup here, and we'll go ahead and get started. Julia.
All right, good afternoon, everyone. Thanks so much, Charlie, for introducing this. So we are the last session between you and the drinks, but that's why we have an all-star session here, and we're going to have a good technical panel. Just, we have very little time, so I'll go ahead and present the first presenter, and it's Deepak Ramasubramanian. He's the senior technical leader at EPRI. Go ahead, Deepak, take it away.
Thanks, Julia. Okay. Hey, everyone. So I'll be giving a presentation today on some of the stuff we've been doing on moving a little bit away from the transmission system and looking more on the distribution side, but then seeing how does the distribution DER and the resources there, what kind of impact they may have on transmission, and what kind of impact they may have on distribution itself. So is there any value proposition to have grid forming in the distribution system, or can the distribution companies say, transmission is going to take care of it. We don't need to look more about it or into that. Just some acknowledgements. There's a lot of projects that fund this work, and just want to acknowledge them. There's a lot of work that we do on grid forming. So the topic of grid forming has these different aspects associated with it, that we have model development, lab testing, controls analysis, education, standardization, and so on. And the work that I'll be talking about today actually spans many of these topics. So it's not very easy to really touch upon any one of them. This is probably the most important slide, I feel, for this presentation. Those of you who heard me in the spring meeting and have heard me before may know that I don't like using the term now grid forming or grid following, although my slide title had it in it. But the reason for that is this aspect of grid forming and grid following is usually can be considered as bookend controls. And there's really a spectrum of control that lies in between. So you go from the top end where you have what would be a legacy inverter-based resources that had only active power injection and no reactive power contribution, essentially unity power factor operation, no grid services, and so on. That would be, in my frame of mind, what would be our quintessential grid following. They don't do anything else for the network. They just inject active power. And as you go down that list, you go into the conventional IBR. Those are a lot of IBR that would be connected in the past few years, have the ability to provide frequency response, voltage response, but over a longer time frame, a couple of seconds. Then you go into something which I'm going to be calling as enhanced IBR that can provide this response over 1 second, full delivery of response over 1 second. And some of these enhanced IBRs by themselves, maybe they cannot tolerate the loss of last synchronous machine, but if you actually put a group of them into a system, then they can improve the reliability of the system, improve the stability of the system. And finally, at the entire bottom is what I would be calling a future IBR that is capable of black start and single-handedly can probably survive a very extreme event. Now, across the spectrum is where you would see that most of the power networks today are probably at the legacy stage. There's few of them that are at the conventional stage. Yet few lesser of them are at the enhanced IBR stage, and then there's only some island networks that are looking at this future IBR. So if you look at this, then what's at the top would be grid following, GFL, and what would be at the bottom is grid forming, where the spectrum lies from providing no services at all to providing all services. So these are these two theoretical bookends. And in reality, we want something in between. We want the inverter-based resources that we want on our system to probably be somewhere between enhanced IBR and future IBR. Depending upon the nature of the system, you might have more future IBR or more enhanced IBR. Depending upon what other resources you have, you can also have this. This figure will probably reappear in almost every slide that I have, because it can help keep the context of what kind of IBR we're going to be talking about. And we're not going to just talk about two bookends of grid following and grid forming. We're actually going to be talking about this entire spectrum, because it helps us align what kind of services these different resources are going to be providing. So a condensed version of this figure will appear in every slide. So what we're essentially trying to evaluate is, how does the transmission system get impacted by DER? What role does load dynamics play? If DER in the distribution system face stability challenges, then is it the responsibility only of the transmission system to help those DER, or can the distribution system also help support their own? Now, some of the reasons why these questions are structured like this is because from EPRI's utility member side, we've got these questions. There are a lot of utility members who ask us that, okay, what's the value case for grid forming in the distribution system if you're not in a microgrid setup? If I'm going to be continuously grid connected to the bulk power system, why do I need these future IBRs on my distribution network? If I'm not going to island, I'm not going to be in microgrid, why can't the bulk power system help me? So why should we take the responsibility? Why should we try to incentivize these resources on the distribution network? So that's the background behind why some of these questions are structured in this manner. Now, we'll walk through a bunch of different studies that we have. We'll start off with this microcosm system, wherein we have a representation of bulk power system connected resources, feeding power through long transmission lines to a load center. The load centers themselves are represented in aggregate. There's a whole bunch of dynamics associated in them. And then we look at a few different scenarios between having conventional IBRs, enhanced IBRs, future IBRs, and also trying to understand the importance of having load representation in different kinds of fractions, different kinds of characteristics. And what we'll see is that depending upon how you represent your distribution system, depending upon how you represent the characteristics on the distribution system, when you make your assessment on the transmission system, you can have a bunch of different response. If you have all your load represented as static constant power load, which your net load is represented, so the transmission system is not seeing the impacts of the distribution connected resources, then you can have a very conservative result. If you have that represented as static constant current and constant impedance load, then you can have a very optimistic result from the transmission side. But actually, if you start representing a lot of these dynamic characteristics, especially if you look at the induction motor load characteristics, you look at the distribution connected resources and their characteristics, then you start getting a very mixed characteristic in between, which means that now this has the potential to impact both the transmission connected resources and the distribution connected resources, with DER experiencing instability, not just because of the transmission connected system, but also the distributed resources in the system. We took this one step further from a microcosm system to a realistic network. We represented only a portion of the realistic network. And here again, we looked at different kinds of fractions of dynamic characteristics of load and DER. And we found out that how different percentages of load versus DER can actually impact the stability of the DER itself, which means that irrespective of what happens on the transmission network, DER on the distribution network in a grid connected mode can be susceptible to instability, which means from a distribution utility perspective, there is a use case to try to incentivize getting more enhanced or future IBR in the distribution system, so that in that local region, they can help themselves, they can help the DER in the distribution system and improve the stability of the system. The burden does not have to be placed on the transmission network, and that itself is a valuable use case. But then how do we go about evaluating what is the kind of resource that you need on the distribution network? What is the kind of comparison between having something on the transmission network versus having something on the distribution network? So we start looking at, okay, if you have only a transmission connected resource, if you have, let's say, again, a similar kind of system structure, you have these conventional power plants that are there, and then you have a distribution feeder that is represented. And you start looking at, okay, what will happen if you lose some rotating machines on the transmission system, essentially reducing the amount of rotating machines that you have. And you try to see, okay, what's going to be the impact on the distribution network. So we have some instabilities coming up. We all like instabilities in these studies because it gives us a chance to provide solutions. And we see that some of these instabilities are very insightful. Stick around for Thursday, and you'll see much more interesting stuff regarding this instability that is coming up in the services task force meeting. There's really some stuff about system strength that we'll talk about in that meeting. But this instability that is there, the distribution connected resources are going to now face this instability. And now the idea is, okay, if you do have this kind of DER, seeing this instability as the system strength reduces, as the synchronous machine reduces on the transmission network, then how does it support themselves? How do they keep themselves going on? How do they ensure that they're going to continue operating? So if we use a transmission connected resource to help the distribution system or help improve the stability, then after a bunch of different studies, which I'm summarizing here, of course, is that we found out that we need around 45 MVA of future IBR that is needed in order to stabilize the network. And that 45 MVA value is dependent upon that location where it's connected, which is called bus number 1 in this particular evaluation. So if you had a 45 MVA enhanced or future IBR connected at the transmission network, you can stabilize the network, keeping those other conventional plants in play. So this is an additional asset, an additional resource that is required. Now, if you actually now consider that you have a larger distribution connected resource on the distribution system, it complies with IEEE 1547/2018, has category B default settings, has volt var, has all the good stuff that IEEE 1547 asks for. And you want to see if this DER has to be stabilized on the distribution network, the capacity of that enhanced or future battery that was required on the transmission network went from 45 MVA up to 90 MVA. So now, if we needed to add more resources on the transmission system in order to stabilize the resources on the distribution network, then essentially means that the distribution network is dependent on the transmission network and the resources in the transmission network and that particular location in order to improve the stability, in order to improve their behavior. So, which means that the more number of distributed resources that start coming onto the distribution network that are not helping themselves, then the burden increases on the transmission side, that the resources on the transmission network not only have to take upon the burden of representing or stabilizing their own resources, but they also have to stabilize the distribution network and those associated load dynamics and all the other characteristics that come up. So if we then shift the burden, let's see what happens if we have to place something on the distribution network. So keep in mind those two numbers about if there was only static distribution, stabilizing the network on the transmission side was 45 MVA of an additional asset. If there was a dynamic distribution network, stabilizing the distribution network using a transmission asset was 90 MVA, so double. Now, if we use the distribution assets itself, I'll skip this because of time. We talked about some of the use cases and we talked about how there are actually distribution networks that are having some of these future enhanced batteries coming into the picture. And we're working with different utility members who have this. But essentially, if we now look at it from the perspective that, okay, what if we have to put in enhanced or future resource into the distribution network, we can do so with a 5 MVA battery instead of doubling the size on the transmission network. So taking the transmission resource from 45 to 90 MVA, instead of that, we can have a 5 MVA battery on the distribution network to stabilize this. Now, we shouldn't generalize all of these results because this can vary from system to system. It can vary depending upon load characteristics and so on. So there's a lot more work that is needed to be done in this space. But this is initial results that help us identify use case and value proposition for some of these enhanced and future resources on the distribution side itself. So if we look at different modes, we needed that resource to be in that enhanced or future mode and not just be in a conventional mode where it can still provide some slow frequency or voltage control. It does have to provide it fast. It does have to probably be capable of black start. It has to have all those good properties in order to stabilize the network. But if it does, then the burden reduces from the transmission side, and we can have some of these resources on the distribution network. So just to close out, that the more we do these kind of studies, the more we look at high inverter-based resource penetration. Firstly, we can no longer ignore load dynamics. We cannot assume the load to be a static component, even if we have different coefficients for it. We have to start capturing the dynamic behavior of load. We have to start capturing the interplay between three-phase induction motor load, single-phase induction motor load, three-phase motor load of different types, pumps, conveyor belts, other types of three-phase induction motor load, stalling of single-phase induction motors and what impact they would have. Can the inverter-based resource provide the fault recovery current for it to come out of the fault? And in addition to that, now start looking at, okay, if you have a bunch of distributed resources connected, then as this instability propagates, what is the burden that we're placing on the transmission system, and how can we alleviate that burden from the distribution system side in order to have improved stability or response? And just a shout out, we do a tutorial on this topic every year. Conducted this tutorial in August this year. The slides are available publicly. So if you're interested, feel free to take a look at this. And with that, I'll close out. We also have a roadmap document that we have to show what kind of studies can be done to look at the adoption of these future resources. That's also something that's publicly available on our website. So if you're interested, take a look at it. And that's it.
Thank you so much, Deepak. Very interesting. Right. So the next presentation is from Wallace, Kenyon. He is Power System Simulation Lead at encoord, and he'll talk about future role of hybrid simulations in assessing the dynamic stability of inverter-based resource-dominated power systems. Wallace, take it away.
Thank you, Julia. Thanks for the introduction. This is really exciting to be here. The last ESIG event I was at was in 2019 in the spring, and it has definitely grown in size quite a bit. And it's quite exciting. That was actually my first and last ESIG event, and it's quite invigorating to now be up here presenting. At that point, I was just a presenter. With that in mind, I thought I would give just a brief history of who I am before we dive into hybrid simulation approaches. Again, we're in the GFM development panel. I'm not going to talk too much about GFM. I've done plenty of work on it, but this is more about how we're simulating our systems, right? So a little history on me. I worked at the National Renewable Energy Lab from 2017 to 2022. Did a lot of work on coupled T&D simulations with folks in this room. Did a huge amount of work on EMT, electromagnetic transient modeling of the Maui power system, which is going to sort of inform and provide an impetus for looking at different ways to do dynamic simulations. I did a PhD at the University of Colorado, where I was absolutely fascinated at the capability of nonlinear frequency control of grid forming devices on power systems to sort of really kind of rethink how we do frequency management on power systems. It's quite fun. And now I work at a company called encoord, that stands for Energy Coordination. We do energy systems modeling in a variety of different domains. And if you want to talk more about that, please come and see me after. So power systems are changing, right? This is why we're all here. I think most of you have probably seen this chart here up on the slide, or some iteration of it. It's been updated. This is the 2019 version. I think the 2018 version came out actually in a paper that I wrote way back in the day. So it's exciting, right? We have renewables that are being integrated to the power system. We use inverters to do this, right? Because these are usually DC sources, and we have to create AC waveforms to provide to the power system. So we call these inverter-based resources, IBRs, right? And we have annual energies that are changing on these systems, which is to say that we're getting more and more energy from these IBRs throughout an entire year. That's a really important metric, and it has a whole host of its own challenges. But the challenges we're interested in today are the ones that are associated with the power that we get from IBRs at any particular instant in time, because that has a very different impact on the system. We're bumping more into the stability domain. And as we achieve higher and higher instantaneous powers, Maui at 76% in 2019, it's much, much higher now. We're going to talk about Maui more. We start to see different types of stability issues. And there's actually an entirely new classification for stability known as converter-driven stability. We're all familiar with rotor angle stability and voltage stability and frequency stability, sort of like the triad of classifications. Well, now there's converter-driven and resonance stability. Converter really encompasses all of these challenges that are associated with the interaction of these inverters amongst themselves. And oscillatory events have been viewed in real-world power systems today. Of course, Kauai comes out. They had the 18 to 20 hertz oscillation in 2021, which was caused by the interaction of, you guessed it, inverter-based resources. So things are changing. It's exciting. But it also means that we may have to start to think a little bit differently about how we approach the simulation of these systems, right? So we have to look at the devices that we're modeling and what's relevant to the devices and what was relevant to the tools that we designed 50 years ago that we still use today, 30 years ago, the many different versions of these tools. And it's good to take a step back and ask, what's going on with these simulation tools? And it turns out that a lot of them were informed by the dynamics of synchronous generators. So synchronous generators are where the majority of the power came from throughout, hitherto now the history of the power system, right? Rotating machines. You could consider these to be partitioned, sort of natural timescale separate dynamical systems, right? I have a governor that regulates a turbine. I have an exciter that regulates the current in the rotor circuit. I have a power system stabilizer that regulates inter-area oscillations by augmenting the exciter voltage outputs. So this is really nice, sort of predictable timescale separation. You might say they're physics-dominated dynamics. Of course, everything's dominated by physics. But these ones are more partitioned. The rotors yield deterministic local frequencies for the buses. And this works really, really well with the contemporary approach for dynamics, which is colloquially known as phasor domain. I like to think of it as quasi-static phasor, QSP, PSSE, PSLF, power factory. Those sorts of tools do this phasor domain analysis, right? Which works really well with synchronous generators. But when it comes to inverter-based resources, these are very different devices, dynamically different. We could consider them to have a much larger bandwidth as compared to synchronous generators. This is caused because the canonical configuration of inverter-based resources, of course, there's a lot of proprietary things going on, but generally speaking, you have cascaded proportional integral controllers. So there's no real natural separation here. Current controllers are, in fact, intended to regulate the dynamics of the filter elements, which is to say that there's feedback from these filters, these inductive elements, and they interact with the current controller. That's why it's there. So mathematically, when we take a step back and look at IBRs, you start to realize that there are going to be times where the IBR dynamics tend to negate some of the simplifications that make the bedrock of QSP simulation tools. So where does that leave us? Well, I'd like to tell you a PSCAD story, the simulation tool to save us all. That's a joke, by the way. Power systems computer-aided design. During my time at NREL, I spent a whole lot of time building a Maui power systems model. If you're going to build a model in EMT, you're going to have to build generic models because in this model of the Maui power system, there was a huge amount of distributed generation that had to be modeled with inverters. So we made these open source models. They're out there. You can use them if you like. They work in PSCAD. PSCAD stands for Power System Computer-Aided Design. They have filters. They have current power voltage controllers as applicable, grid following, grid forming, limiting DC side dynamics. They're generic, so you will have to change the parameters to fit your device, but you can use them if you like. So what did we do with these models? Well, we created a system that represented the Maui power system, a virtual dual, you might call it. So the Maui power system is not very big, 200 megawatts, absolute peak. It's even less than that, but I'll use that. It's a nice round number. About 200 buses. Pretty much every single bus on this system had distributed generation, so we had inverters. I'm not going to go into the details. You can look at these slides later, but there's a whole bunch of different devices going on. And we built this in PSCAD with generic inverter models. We validated it to field data. What does validate mean? It means that we looked at an event that had a perturbation. In this case, it was a fault on the generator service unit transformer. The generator tripped offline afterwards. So we had a nice voltage perturbation and a frequency perturbation afterwards. And we validated our PSCAD model to the field data. But I would like to emphasize that even though this model was parallelized on 30 cores with a dedicated machine, it still took hours to run a 15-second simulation, 3 hours. It's a very long amount of time if you're trying to assess the stability of your system. So now that we had this model, we wanted to do some comparisons. PSSE was a likely suspect because we had a PSSE model of the Maui power system. So the chart here that you're looking at from S1 to S7, really we can just consider that as a marching forward and taking voltage forming devices off of the power system, right? In scenario 1, great agreement between PSSE and PSCAD. reduce the MVA rating by taking off synchronous condensers of our system, and we start to see some differences. PSSE is having numerical issues and or not able to complete these simulations. Maybe it's a tuning problem, maybe the models need to be updated. It's hard to know unless you have the results to look at. PSCAD was showing this high frequency oscillation, 6 Hertz. This looks like a suspicious PLL interaction with a power controller probably. But it's curious to think about how PSCAD was telling that there were oscillations there. PSSE wasn't really giving us the result. So which one do you take as the correct result, right? Now it's easy to say PSCAD versus PSSE, but why not just make PSCAD versus itself, right? It's hard to compare 2 different commercially available software tools that are designed to do different things, right? They're not designed to do the same thing. That's inherent. So what we did is we looked at reducing the complexity of these generic inverter models. We said, well, we could take away the filter in the current controller and then just apply a current reference to PSCAD, right? You might end up with sort of a device level QSP proxy in this case. And that way we could say, well, if we're not modeling the filters and not modeling the current controller, are we going to see something different? So we wanted to look at that. Of course, all of these have a phase lock loop because if you're doing 3-phase point on wave simulations, you have to have a PLL so you understand what angle you're actually going to use to inject current. So we did a systematic reduction of all of the DG devices on the system. So 170 devices, about 100 MVA rating. And what did we see? Well, if we brought the system to the dispatch of that scenario 3 where we saw all of those oscillations in PSCAD, we found that in the power loops control, which is to say when we had the filters and the current controllers taken out, the oscillatory element was quite substantially damped. In fact, you might even say it's not present, but there are a few periods in there. Of course, it persists in the PSCAD one. We knew that was going to be there. So it begs the question of which one's right? Why did we see it there? As an anecdote, since this is a GFM panel, I would say that if you park a GFM device on this Maori power system, it does fix those oscillations. Gets even better if you use nonlinear droop. So where does this leave us? System-wide EMT type simulations are an enormous effort to develop and extremely computationally intensive to run. That goes without saying. The Maori system is not a big system, 200 megawatts. The Western connection is about a 200 gigawatt system, so that's 3 orders of magnitude larger. But some of the bedrock simplifications that are inherent to QSP type simulations are also simplifying pertinent controller-driven dynamics. But again, QSP approaches are still vastly applicable, as we saw in those scenario 1 and scenario 2 events. Those were good approximations, at least as far as matching the results of the 2 simulation tools. But there are undeniable operational periods when you need to have the detail, right? So we could look at simulation. This is the exchanging of data between tools. So if I have 2 commercially available software tools like PSCAD and PSSE, can I carve out regions of those networks and model them in PSCAD and then model the rest of the system in PSSE? EMT detail when it's needed, QSP when it's not. I mean, there are a lot of people working on this. I have good friends who are working on this and making good progress in this domain, but it's challenging because these are separate simulation tools. They're separate software tools. Interacting between those 2 is always going to be challenging from a data perspective and also a language perspective and output perspective. Boundaries. Where do you draw the boundaries? That's the real big question. If you're using 2 different tools and you have to curate the models of the reduced networks that you're actually modeling, then it's going to be a huge effort to revalidate and or create those networks as those boundaries are changing. And of course, we know that the penetrations and or the metrics we might be applying are going to change during our operational conditions. And finally, how do I handle the interfaces? You have to create a network equivalent. I can't just separate these 2 simulation tools as independent entities. If I'm simulating in PSSE, I need to have a proxy for what my PSCAD model is, right? And vice versa. So the research that I've been doing is focused on hybrid simulations. And hybrid simulations are akin to co-simulation. But the idea is that we're actually looking at our entire dynamical system and we're making adjustments as the simulation is passing. For instance, in that 3-hour Maui simulation, of course, there were instances of adaptive time stepping in there. But what if I was also looking at the reduction of order of those models? I didn't mention it before, but actually, when I ran the simulation approximating the filter and the current controllers, it was about a 50% reduction in computation speed. So there would have been a lot of savings if I had known that I could reduce those devices when I didn't need that detail, right? There's a nice little image up there to show you what's going on. The yellow trace would be sort of an interesting representation of the computational cost of an EMT type simulation. You can see it's going to the right and up, so it's getting larger. The blue one could be representative of a QSP. Of course, QSP is missing detail, EMT is taking too long. But if I was able to vary how much was modeled in an EMT type simulator versus a QSP type simulator, then I would have sort of that green trace in there. That is, of course, a huge simplification, but I think it gets the idea across. So we were recently received a National Science Foundation Small Business Innovative Research Award to look into this, to build a hybrid simulation tool. And there are 3 things that we're trying to look hard into that are foundational to whether or not we could really proceed and create a tool like this. One of them would be intra-simulation detail modifications, which is to say, if I have full order models, if I have the power and current models, can I do some sort of like singular perturbation on the fly? Hopefully there are no mathematicians in here. They'd get really upset. Kidding, no, it would be interesting though, because singular perturbation is the bedrock for creating our differential algebraic equation sets, right? And if I'm treating this epsilon value, which we usually take to 0 as a time changing thing, it's a function of time of simulation, then I could look into that. Another aspect would be if I am doing all of this natively within a single network, can I do autonomous boundary identification? We could be applying some metrics for partitioning, or we could be doing analysis on the results of the simulation and looking at high frequency components or larger states rate of changes. You can see how the boundary, emphasized by that little dotted circle there, could be getting smaller. So not only could we maybe be reducing the detail of our models, but we could also be reducing the size of the network that's being approximated in the more detailed space. Finally, what does the computational structure look like? That would be a substantial challenge, but it also, it begs the question of, does this interface handling that you would have to do if you're doing co-simulation, would that be handled inherently within the computational structure? Some nice math up there too, but I'm about to run out of time. So the last slide, we're doing research on this because we've recognized that there is clearly a deficit. We need detail in these high RBR share operational periods. But the simulators that are available that do that sort of detailed simulation are vastly far too computationally intensive. So we're looking at new ways to approach this. And then we could roll this into our existing commercially available tool known as SAINT, which does optimization in physical network simulations. Thank you. That's it.
So the next up is Julian Leslie. He's a head of networks at National Grid ESO. You heard from Julian yesterday talking about some of the developments in GB around integration of inverter-based resources. And today he'll be talking about NGESO's experience with inertia monitoring and measurements. Julian, take it away.
Thank you, Julia. Good afternoon, everybody. It's great to be back on the stage again. So I am Julian Leslie, Head of Networks and Chief Engineer for the GB Electricity System Operator. So we can do all this modeling. We heard a lot about it yesterday about modeling. We've heard a little bit more about modeling now. But actually, what happens in real time and how do you really know what is happening? Because you can model the peak, you can model the trough, but obviously the system is now so dynamic. What is happening in all those intervening periods? So I'm going to talk around some of the changes that we've made and the link between frequency management and inertia, and how, as you sort of operate closer and closer to that cliff edge, how your situational awareness needs to improve so you know where that cliff edge is and how close you are, and make sure you don't step over it. So, as we know, nothing new on here. We are decarbonising very rapidly. As I said yesterday, 3 times this year, we've been at 90% zero carbon. We've had 70% penetration of IBR on the network. So this is a real issue for us. We are progressing and we're on track that in just a year and a half from now, we will have 100% zero carbon generation for a few hours at least in 2025. So we need to be prepared for that. We need to make sure our control room operators are prepared and they have the tools and awareness that they need. You can see how, as we've decarbonised the system, how the changes in inertia have fallen over the system. So in 2009 is the purple at the top, and then the yellow in 2021. And obviously, that was 2 years ago. So you can imagine if we drew this graph today, it would be even lower. Obviously, the big thing in here as well, what we don't really know, is the contribution of inertia by the distribution system. As industry is closed, through the economic downturn, as industry changes their motors from synchronous to asynchronous motors, what is the impact of all of that? So we make assumptions in our models, but they are just assumptions, and we need to sort of move away from that. So the average inertia that the market provides us is around 180 GVA seconds. I know it was a debate, an international debate, is what is the measurement of inertia? We use GVA seconds. It's just a number, right? So the average is 180. We have a minimum currently of 140 GVA seconds on the network, and we're trying to drive that down to be 100 GVA seconds so we can manage a stable network. So there's ways we can do that, right? So you either increase your inertia or decrease your inertia, but increase your frequency response time frame. So this graph here really demonstrates the value of what I spoke briefly about yesterday, the dynamic containment frequency, fast frequency response product, which is provided by batteries that delivers all of its output within a second. And it's dynamic. So the quicker the frequency is falling, the quicker it responds. Then as a frequency recovers and it sort of controls itself so you don't get the overshoot that you might do historically. So the graphs here you can see on the dotted line is just using our normal primary, secondary, and high response. So that delivers primary within 10 seconds. You can see that with the impact on the solid lines, that using the dynamic containment where it delivers all of its output in a second, that actually you don't get the fall in frequency. The frequency is arrested very quickly and comes back to a very stable position extremely fast. And you can see that happens at all those different sort of inertia levels, that the performance of dynamic containment, I think, far exceeded anything that we ever modeled in the system. And it's been enabled us to reduce our frequency response in the system. It enables us to move more rapidly towards reducing the amount of inertia we require in the system. And the way we provide inertia in the UK currently is if we need for a short, we curtail the wind because the wind has provided a balanced market. So we need to turn off the wind to create the headroom to bring on gas. So for every GVA second that we can save on inertia means that we can allow the renewables to run and we're not burning gas at the same time. And that is the key principle that we're using as we move towards 2025 to get to 100% zero carbon. So your very fast frequency response, we spoke yesterday, there was a session on that, crucially important. The other thing we're doing here, which is really helping, is that we also have what we call dynamic modulation. So dynamic containment is a post-fault product. So you have the loss of generation, frequency falls, delivers its output in a second, as you can see on the graph here, very well controlled. However, you don't know where we're starting from. The frequency could be 49.8, could be 50.2. So therefore, that changes the amount of dynamic containment that you need to carry on the system. So our new product that went live this year is dynamic modulation, which is a pre-fault product. And what that is, it's a whole bunch of batteries trying to keep the frequency very close to 50 hertz, keeping a very tight tolerance. So you always know now when you have your fault, when you have your largest loss of your largest in-feed, you know the frequency was close to 50 hertz. Therefore, you're not having to worry at starting your frequency loss of 49.8. Therefore, you can carry less dynamic containment and less frequency response. So the new products using the fast-acting IBRs that we've just been talking around really give us new tools and new ways of thinking about how you manage the system. And it's cheap. When we started 2 years ago with dynamic containment, to stimulate the market, we paid £17 a megawatt hour for this response. Now we're paying £1.50. So less than $2 for every megawatt hour of frequency response. So together with the fast frequency response, we've done dynamic containment, the reduction in inertia. We also spent £50 million changing the protection devices on 25 gigawatts of embedded generation. We now save £1.8 billion a year. So $2 billion a year in managing frequency and constraint costs on the system because we have dynamic containment, we can reduce the inertia, and we change the rock-off ratings on 25 gigs of embedded generation. For £50 million, we save $2 billion a year forever. So the new tools that we have facilitated by IBRs, facilitated by low-cost batteries, there's been a real game changer for us. However, we're getting very close to that cliff edge I mentioned earlier. So we need to give the control room operators that real clarity as to how close to the cliff edge they are. So historically, using inertia, we've done a simple calculation you can see here on the screen, but it is a point in time. It is using assumptions around the measured or the calculated inertia of these items. Combining that with what happens in previous trips, so then you can make sure you can calibrate the whole thing. But again, was the trip at a low inertia period? Was it at a high inertia period? Therefore, the results can be a bit suspect. But it served as well because we had plenty of fat in the system. But as you erode all of that fat, you're getting closer and closer to that cliff edge. You need to do something different. Because this is new, we went with two different technologies. We were using a GE technology in Scotland, which is using PMU data and is using the SCADA system in order to see what is on the system and then doing a calculation as to what the inertia is. We're also using the reactive technology solution, which is a 10 MVA supercharged capacitor located in Teesside in the northeast of England that pulses the 10 MVA charge onto the system at very precisely timed sequencing. With the measurements then using these XMU devices all over the UK system, that actually, because you know what the injection was at a very precise time, you can measure what the impact is across the network, and therefore, based on what the input is, what the response was, you can calculate real-time inertia. And therefore, that's removed all of the assumptions around, well, what is the demand contribution to inertia? What is the actual contribution of that 30-year-old gas-fired power plant that's operating on the network? We don't need to know that anymore because we have a real-time measurement. And therefore, we're making clearer that line in the sand, that cliff edge, and we can know really where we are at every second of every day, not just on the peak and in the trough. So it's been an absolute game changer in terms of understanding inertia on the system. But now, because also we've got this millisecond by millisecond measurement, we're also seeing and being able to monitor the oscillations, another phenomena that is happening on the grid system that we've just been unaware of until now. But now we have the ability to see that in real time, then understand what it was that was causing it and take action to prevent it in the future. The GE system is different to the reactive technologies one in terms of it gives you a real-time measurement as where your inertia is now with a bit of a confidence range, which is what the sort of the yellow shaded bit is there on the left. The beauty about the GE one, though, it gives you a forecast as well because it knows what the forward schedule is of the generation. It knows what the forward demand profile is going to be. And therefore, the blue shaded bit is where your inertia could be as you move forward in time. So it gives you that forward view as well. So again, from the control room point of view, they can be dispatching other inertia products in order to increase inertia on the system if required. The reactive technologies one, it's a little different in terms of what it shows you. It's a real-time measurement. Again, there's a confidence factor around the number because this is such a unique and so many variables coming in there. But because this is a real-time measurement, there's a lot of focus on this because there isn't assumptions in this. This is a 10 MVA squirt into the system and then measuring the outcome. We're still building our confidence with this. We're still sort of working with the control room, comparing it to our offline tools as well, just to make sure that the calibration of the results are accurate. But on the whole, the trace and the inertia that we've assumed over the years closely aligns with the measurement the reactive technologies is giving us. And the beauty about the reactive technologies one, your 10 MVA injection into the system, at the lower inertia periods, that's a bigger injection. Therefore, the size of the change in the MVA across the system is bigger, and therefore the measurement is even more accurate. So just at the time you really need a more accurate solution, that is the time the reactive technology solution is given as a more accurate position. So this is allowing us in the control room to save money because we're not having to, we know where the inertia is and therefore we can buy accurately in the market. We can curtail fewer megawatts of wind and buy fewer megawatts of gas to provide that inertia. It also means that when we go to market through our Pathfinder projects, we know how much inertia we need to buy. So we know how much grid forming inversion we need to buy. We know how many synchronous condensers that we need to procure in the market. And we're not over procuring, we're procuring just enough. So again, it's good news for the consumers, and it's great news for the control operator. For the first time, they can see that cliff edge. So as we look ahead, though, yeah, we have this data, we have this tool. Some of you in the room will be aware that we had some oscillations over the summer created by the commissioning of some very large offshore wind farms. And what this data is doing, because it's real time, it's fed into the control already, it gives us a real opportunity to understand what is happening on the network. So that either post-event, we can see and look back and see the very details of what's happening. Or for the control operator, they can see what is happening on the background and get comfortable with the fact that there are these 2 Hertz oscillations every time we open a breaker. But there are these other oscillations that naturally happen on the system, but we've never seen before. But giving that transparency to the control operator, getting them comfortable that oscillations do occur. But when you see something like you've got on the screen right now, that is out of the ordinary, and there's an issue that we needed to solve, it really helps to pinpoint with the very accurate timing, pinpoint where it started, who was the cause of the oscillation, and then you can focus in on your actions to fix it. So that was all I was going to say this afternoon. So I think the summary is, though, better transparency, knowing where that cliff edge is, really linking together your frequency response with the inertia on the system and making that trade-off for your particular part and your particular system. Do you have a little bit more access to more low carbon inertia, therefore your frequency response doesn't need to be as quick? Or do you not have access to inertia and therefore your frequency response needs to be quicker still? And then you can reduce the amount of inertia you need on the system. So with that, I will leave it there. Thank you very much.
Thank you, Julian. The next up is Shahil Shah. He's a principal engineer at National Renewable Energy Lab, and I think he'll continue a little bit of topic that Deepak has started. We'll talk about parallel operation of grid forming, grid following, and synchronous machines. Shahil, take it away.
Yeah, thanks, Julia, for the introduction and for the invitation as well. Discussion around oscillations always excites me. So the reason we are talking about grid forming is we want to operate power systems with more and more IBRs with less and less synchronous generators. And what I'm going to focus in my talk is what really we need from grid forming IBRs to enable that functionality or to enable that future, and how can we quantify that. So for that, I'm going to talk about 2 real-world case studies about what we really need from grid forming IBRs. And then in the second part, I'll talk about how we quantify that need. So the first case is about oscillations that occurred in Kauai, which is an island in Hawaii, where if you see in the map, there is this red dot, which is basically a conventional power plant, which was supplying 60% of the load, and rest of the resources in that system were IBRs. In November 2021, that conventional plant tripped, which was supplying 60% of the load at that time, and it resulted in a lot of these oscillations. Now, the question is, when you lost 60% of the generation, are these oscillations some nonlinear phenomena? There are interactions among IBRs. Who is really causing these oscillations? So after doing some impedance scan studies, we figured out that some of the IBRs in the system did not like weak grid operation. So this is just one IBR connected to a single machine infinite bus format, and just showing that for a weak grid condition, when the short circuit ratio is small, the system ran into oscillations. So yeah, no news over here, right? The conventional IBRs don't like weak grid conditions. Some of my NREL colleagues like Andy Hoke or Gene Tan can talk about how KIUC or Kauai is basically addressing this problem by converting some of the IBRs into grid forming. But the key point here is that some of the IBRs didn't like weak grid conditions. The second real world case that I want to talk about is in Australia, where the situation was even more interesting. They have been seeing this 17 to 20 hertz oscillation since August 2020. They are still occurring very frequently, sometimes in the presence of event, but many times without any event. without any disturbance. System runs into oscillations. And the map that you see here, those dots are actually basically indicate solar farms. So there are a bunch of them. The shaded area is really the West Murray zone, basically in southern Australia. So now the question is, who is causing these oscillations? And we worked with AMO to understand the root cause of this oscillation stability. And they were not able to figure out just by looking at measurements where these are coming from. They're able to reproduce it even in system-wide model, but still in system-wide model, they're able to reproduce it, but not understand the source of these oscillations. So again, we did the impedance scan study, found out that some of the IBRs in that region didn't like the weak grid condition. As you can see I won't go into how to interpret this impedance scan plots, but the takeaway here is that for short circuit ratio of less than 3, some of those IBRs, they were running into this instability at around 17 Hertz. And that was the cause of instability. But here's the question. If weak grid condition is the problem, then why these oscillations are occurring without any disturbance? Because traditional understanding is that we will go into weak grid conditions when we lose some line or when we lose synchronous generators. Basically, the source is either the source of grid strength or basically the pathway transmission line to bring that grid strength to IBRs. So why we are seeing these oscillations without disturbance? And by looking at the impedances or impedance scans of a whole system, which actually takes a lot of time to run in PSCAD with a full grid model, it takes around 4 days to get one of the scans that you see on your screen. So here what you are seeing is in the plots, the black trace is impedance of the Australian grid seen by one IBR for a particular operating condition. The pink trace is the same grid that the IBR sees for a different operating condition. And nothing has stripped. There's no transmission line has stripped. There's no synchronous generator has stripped. But still, the grid characteristics look significantly different. Now, if you look at the conventional metric of grid strength, which is short circuit ratio, basically the impedance at 50 Hertz or fundamental frequency, they're exactly the same for both plots. But for operation condition 2, the grid strength at other frequencies, particularly at 50 plus 23 Hertz, so basically at 73 Hertz, is significantly poor. You can see this resonance or the impedance. What is really happening is that some of the IBRs for certain operating conditions are deteriorating grid strength for IBRs in its proximity, and they are causing this oscillation issues. Now the question is, would you call it a weak grid problem or control interactions among IBRs? Because although this particular IBR where we are seeing this type of grid doesn't like weak grid, but the weak grid is created by other IBRs, not because the system itself has a grid strength problem. Well, whatever we call it, but the problem is basically the grid strength. So 2 aspects of grid strength. First is grid following IBRs, they don't like weak grid conditions, and they also sometimes deteriorate grid strength. So it's not just about that they have problem operating with weaker grids, but sometimes, not always, but sometimes at certain frequencies, the grid strength might be very poor basically they deteriorate for IBRs in its proximity. So what we want from grid forming IBRs to enable system where we have higher and higher amount of IBRs is they should be able to operate in weak grid conditions. Also, they should be able to improve grid strength for IBRs in its proximity. And these are some of the specifications that AMO is including in the grid forming voluntary specifications, that not just weak grid operation, but the grid forming IBRs should improve grid strength. So now how do we translate this system need that grid forming IBRs need to improve grid strength in a quantifiable specification, right? So that is what I want to focus on next few minutes. So really the grid strength is about the voltage stiffness, or basically the ability of an IBR to hold its voltage constant. That's how we define grid forming, right? So the core grid forming functionality, I would argue, is basically the voltage source behavior for fast time scales. The reason I'm putting this jarring title, like what is not grid forming, is just to make a point that the other functionalities like black start, short circuit current contribution, primary frequency response, power balancing. These are all good to have, but they are not really what helping the grid strength. They are more steady state phenomena. Like we don't expect nuclear units to provide a droop control or primary frequency control. We don't expect all synchronous generators to be black start capable, but they are still all grid forming devices. So the point is that from the grid forming resource to provide the strength, grid strength, we are really looking for this voltage source behavior. Now, how do we quantify that voltage source behavior? So let me show you, make this point one more time using a real experiment that we did at NREL, like why the core grid forming functionality is really the voltage source behavior. So we ran this island grid. It has a inverter, the battery energy storage system with 2.2 MVA inverter, which can operate in both grid forming and grid following mode. It has one synchronous condenser, which can also be operated in synchronous machine, and a load bank, 3 megawatt load bank. All these are real devices, and the grid symbol that you see over there is actually from a grid simulator. So in this particular test, the island test, what we did is first we removed the grid simulator or removed the grid, and to see how the inverter, synchronous condenser, and load, they are together balancing the grid and supplying this load. And in the second stage, we remove the synchronous condenser to see if the inverter is capable of maintaining this island grid or not. So when the inverter is operating in the grid following mode, particularly the left-sided results, if we apply step change in the load, if you see the synchronous condenser, the red trace is really supplying that majority of the load in the initial part of after the disturbance, and then grid following battery energy storage system takes up the load because synchronous condenser cannot supply the mismatch between load and generation in steady state. So here the synchronous condenser is really stabilizing the grid. The grid following is actually doing the power balancing part. As soon as we remove the synchronous condenser, the bottom left plot, the grid disintegrates or becomes unstable. So again, really this shows that synchronous condenser, which doesn't have any headroom, steady state headroom, the power dispatch, is holding the grid by just acting as a voltage source. On the right is the same test when the inverter was operating in grid forming mode. So for step change in load, both inverter also now acts fast instead of just acting in steady state. It acts fast and takes up the load. And when the synchronous condenser is stripped, the inverter is able to maintain that island grid. So because it has that voltage source behavior. So now how do we quantify this voltage source behavior to define specifications around it so that grid forming IBRs can provide the grid strength that we are looking for other IBRs, conventional legacy IBRs in its proximity. There are two ways to do that. Time domain testing, where we expose the IBR to different disturbances like a phase jump, voltage jump, frequency jump, and see how it reacts in the active and reactive power output. The challenge with this approach is that the response is hard to specify or quantify, like develop specifications around it, because the response can change with different grid conditions. For example, if you have a very strong grid and you do this test, the inverter will dispatch a lot of active or reactive power depending on the disturbance because it doesn't have any impedance to fight against. Now, if you do the same test with very weak grid condition, there's a lot of impedance in front of inverter. It might not react the same. Now, how do you specify? Do you specify for weak grid or you specify for strong grid? The other approach is doing the same thing, basically response from voltage disturbance to reactive power or frequency disturbance to active power, but do it in the frequency domain. Use the transfer function, basically scan transfer functions from voltage magnitude to reactive power output or voltage phase, basically grid voltage angle phase to active power output, and you can still get the same similar specifications. If you look at the plot on the right, it's a low pass filter. The gain is flat within the fundamental frequency between voltage magnitude to reactive power, and the phase is 180 degrees. What it shows is that if there is a voltage dip, this IBR will dispatch reactive power, will increase the reactive power and proportional to the voltage dip. So that explains the constant gain. And the phase is 180 degrees because of opposite relationship. Like if the voltage goes down, you want reactive power to go up. So this constant gain at low frequencies below fundamental frequency and 180 degree, constant gain below 60 hertz and 180 degree phase below 60 hertz are really the fundamental characteristic of voltage source. So we can define this voltage source behavior or grid stability or grid strength improvement functionality by using this frequency scan. So here is one example pass-fail criteria of an IBR, whether it's a grid forming or not. So if this Q by V frequency scan within a frequency range, say 4 to 40 hertz, because we don't want it to hold the voltage phasor constant in steady state, so we don't care about less than 4 hertz. If it is flat and if the magnitude is closer to 180 degrees, then it is a grid forming resource. It is helping you with the grid strength. If not, then it is not a grid forming resource. And here it can be, I don't care about what are the controls inside IBR. This criteria can just look at the terminal characteristic and define if it's a grid forming or not. So here are some of the scans that we have done for different resources at NREL, doing this Q by V frequency scan. There are a bunch of them, and I understand that they're difficult to read, but I would like you to focus on the red scan, which is at the top, which is basically the Q by V frequency scan for synchronous condenser, 2 MVA synchronous condenser that we have. It has a flat response from around 1 hertz to almost up to 40 hertz. The peaking, the flat gain, the 180 degree phase for this red trace, they really indicate that this synchronous condenser is acting like a good stiff voltage source. Now, if you look at the set of blue curves, the solid blue line, which I think is very hard to read, it is quite flat. And that is for a 2.2 MVA battery inverter operating in grid forming mode. And it meets this criteria, like the gain is flat, the phase is closer to 180 degrees as it stays within this box that I'm showing. If you look at the dash dot line, the blue dash dot blue line, that is the same inverter, but operating in grid following control mode. The same 2.2 MVA actual hardware inverter. It's nowhere near this criteria where the gain is flat or the phase is close to 180 degrees in that frequency range. And basically it fails to be a grid forming resource. So if you, similarly, there's a set of green curves which are about a PV inverter, 2 MVA PV inverter, which for solid line, it's a grid forming, for dash line, it is grid following. But the point is that you can really quantify whether the resource is acting as a stiff voltage source, providing you grid strength or not by looking at this frequency scans. We can look at similarly the impedance responses. Instead of Q by V frequency scans, we can look at the Thevenin impedance and understand the difference between grid forming and grid following. Like grid forming, because it is trying to act as a voltage source, you would expect it to have a lower impedance at lower frequencies within control bandwidth, particularly around the fundamental frequency. Whereas the grid following IBR, and here the plots are actual experimental measurements for the same inverter, for blue and red, they are for the same inverter or same wind turbine. So we can also use impedance. Now I get that this a lot, like, okay, how do we do these scans? They are too complex to do it. For that, we have developed a software tool at NREL called GIST, or Grid Impedance Scan Tool. At the bottom, you see the graphical user interface. So user can just bring in models and do this. We are working with a couple of system operators, including AMO, to use this tool to understand the stability and also how we can leverage grid forming to improve grid strength. But to summarize the grid forming part, the main points I want to make is that really we are looking for grid strength improvement from grid forming resources, and the grid strength improvement from grid forming resources comes primarily from their voltage source behavior. And now we can come up with ways to quantify that voltage source behavior, But that is really the core of why we are looking for grid forming. Thanks.
Thanks, Shahil. And so last but not least is from far down under is Behrooz Bahrani. He is associate professor at Monash University in Australia, and he'll talk about transient stability of grid forming resources. Behrooz, take it away.
Thank you so much, Julia. Sorry for my voice. My vocal cords have been playing hide and seek with me, and apparently they are winning. So I will be talking about transient stability of grid forming inverters, and it'll be hopefully an interesting continuation of what we had in the previous presentation about parallel performance of IBRs. We have been looking into that problem to some extent. I will be talking about that a little bit in the presentation. But before I start, this is a part of a larger work that has been funded and initiated by GPST, Global Power System Transformation Consortium, and CSIRO in Australia. CSIRO is equivalent to National Labs loosely in the US. And they've been working with a number of universities in Australia to advance the research agenda that we have been helping them to develop as well in the last couple of years, and hopefully it will be a continuing endeavor. In the project, we've been working with University of Sydney and also EPRI. And what I will be presenting is a summary of the first stage of the work. I'll be starting with a quick introduction, and then I'll talk about transient stability. And finally, some enhancing controls that we've been looking at in order to improve the transient stability of grid forming IBRs. But, well, what is transient stability? Probably it is known to everybody, but a very quick recap. Transient stability is typically the ability of an inverter or an asset generator to go back and recover to a desired stable operating point when it is subjected to a large transient. And it could be like a phase jump, it could be a fault. And fault is typically the more typical disturbance that is used in these studies. It is as opposed to small signal stability, which looks at stability around one equilibrium point. Typically would use linearized models for small signal stability, but for transient stability, you look at a wider range of operating points. When you have a fault in your system, you go to an operating point which is much further from your initial one, and then you want to understand whether you can stably recover and go back to that operating point. Inverter-based resources are typically vulnerable, and they're not they cannot tolerate these larger disturbances easily. So it is important to study that performance, their performance within this transient stability area. So this is what we've been doing, and we've been trying to look into transient stability of grid forming inverters particularly. But again, before going there, a quick recap of a comparison between synchronous generators and grid forming inverters. Grid forming inverters, obviously, there are a number of different ways of implementing them, but the more accepted one, which is a virtual synchronous generator, tries to mimic the performance of a synchronous generator. Typically, they can improve your system strength and frequency stability. But when you look at synchronous generators, they are capable of providing very high fault current. Typically, they can go up to 6-7 per unit, and you typically do not need to limit their current, and they always remain a voltage-controlled asset for you. Well, that's great, but they've got fixed structure, meaning that you cannot do anything with them. There is no flexibility to implement other controllers on top of what you already have. GFMIs, on the other hand, typically you need to regulate the current. You need to make sure that the current is not exceeding a limit, which is typically anything between 1.1 to 2 per unit. And typically we engage some sort of current limiter as soon as we are hitting a particular limit that is essentially the limit of your semiconductor switches in your grid forming inverter. Now, this is not great. That's actually bad, because as soon as you go to current limiter mode, it means that you're going to essentially a current controlled asset rather than a grid forming asset. But at the same time, because you're dealing with inverters, it is very, very flexible, and you can implement enhancing control. So that's a good point about grid forming inverters as opposed to synchronous generators. Now, in the work that I'll be very briefly presenting, we looked into a number of different aspects of grid forming inverted transient stability. We looked into a single GFMI with current limiting device, or current limited actually GFMI. We looked into parallel GFMI, GFLI without current limiter, and also we looked into multi-IBR systems, seeing how we can look at their transient stability. And based on the analysis we did, we had a number of different proposals in order to enhance the transient stability of grid forming inverters. And hopefully I'll be able to very briefly talk about them. But before I go any further, a very quick introduction of the structure that we've used. Like I said, there are a number of different structures for grid forming inverters that you might have seen in the literature, but this one that I will be presenting here is probably the more accepted version, where you typically have an internal current controller which regulates the inverter current control, and the references for that current control is typically given to you by a capacitor voltage controller, which controls the voltage at the point of connection. Now, the references for this voltage controller is given to you by a primary loop. The primary loop is at the same time responsible for generating the frequency or the omega that you would require to go to DQ frame in your current, in your control blocks that you've got. And typically you have a power calculator which calculates the power of the inverter. So based on the power that you calculate and the references that you've got, you then generate the references of the voltage and then subsequently the references of the current. And obviously you might have other loops such as governor, exciter, or other secondary loops, but I haven't shown them here. And we will be only focusing on the primary loop here. Now, if you've got this, if I go back actually one step, the inverter current controller that we've got here, those references that are given to that, if you limit those references, you can protect your switches. And that's how we engage current limiters. So there are a number of different types of these current limiters. One of them is magnitude limiter, meaning that you simply limit the magnitude of the current that you're injecting. One is a deprioritized limiter. You prioritize your D component of the current, and then if you've got any further space, you go for Q injection. And the last one is Q prioritized current limiters, which is essentially the dual of deprioritize. You prioritize your Q injection. Now, each of these types have their own, obviously, impact on the transient stability. But what we studied was Q prioritized limiter, because this is a more accepted, more essentially used version of these current limiters. And it actually helps you to inject some reactive power while you're going through a fault. And the rest of the analysis are done based on this type of limiter. Now, when you want to analyze the transient stability, obviously one way is to use EAC criteria, as we would be using for synchronous generators. And if we didn't have any current limiter, it would be essentially identical to synchronous generators, but we do have current limiters. And what I'm showing here, the blue one is essentially the deceleration region for a grid forming inverter without any current limiter. And the red one, the dashed red one, is essentially the curve, the evolution of your angle when you're subject to a fault. And you have engaged your current limiter. Essentially, where there is actually coming back, the dash one is coming down, that's where the current limiter has been engaged. And you can see that the maximum deceleration region of this current limited VSG is much smaller, meaning that it can become unstable much quicker than a not current limited VSG. Now, you can see that this UEP is essentially unstable equilibrium point, that as soon as you want to cross that, your system becomes unstable. And this is a very simple case study where we had a fault, and we did two tests. One of them a shorter fault, meaning that we didn't pass delta U, and then the other one when we passed delta U. So as soon as you pass delta U, your system becomes unstable and you won't be able to recover. But if your fault is cleared before delta U in this current limited grid forming inverter, you can still recover. Now, when we were looking at this problem of Q prioritized current limited GFM VSG, we realized that in addition to this UEP, that if you pass this UEP will make your system unstable, there's another point that can play a role, and we called it end point. This endpoint is essentially a point that your voltage controller itself might become unstable as well when you've got a fault in a Q-prioritized VSG. Now, in this particular case that I'm showing here, endpoint is happening after UEP. So, well, I mean, the VSG is already unstable. So if I pass delta U, my system is unstable. I don't care whether the voltage controller is stable or not. But there might be cases where this endpoint, where the voltage controller is becoming unstable, happens before the point that the primary loop might become unstable. So that means in these types of scenarios, you will lose stability, not because your primary loop is becoming unstable, but because your voltage loop is becoming unstable. And this can happen in a Q-prioritized grid forming inverter. And these are, what I'm showing here is a time domain test that we have become unstable, again, not because we are passing that UEP, or not because the primary loop is becoming unstable, but because the voltage loop is becoming unstable and it's reaching this endpoint. More information about this particular point is in the paper that I've put here. It's a letter and it's available on IEEE website. If you're interested to know exactly where this point is happening, you can go through. There is a very nice criteria that we've developed for that, and it will tell you when this delta C or this endpoint might happen. Now, we try to expand our activities to a multi-inverter system. Particularly, we looked at a GFLI plus a VSG in parallel, and we try to understand when they can become unstable when they're exposed to a fault. And the fault was happening at the point of connection, the common bus. Essentially, you can look at it as a battery energy storage, which is in grid forming mode, installed next to maybe a solar farm in a remote area of the network. So what we did here with certain assumptions that we had, and none of them were unpractical, they were like practical assumptions. We tried to come up with some sort of analytical or visual type of transient stability analysis, similar to what we would be doing for the SMIP case that I've got here. So this is the SMIP case, but we were hoping to see what happens if we put a VSG and a grid following inverter next to each other. So the two graphs that I'm showing, one of them is a stability boundary for your VSG, and the other one is for the GFLI. Now, if you look at them together, both of them, you can come up with these boundaries, and I'm very much simplifying what we did here because we don't have time to go through all the details. But essentially, what you can get out of this analysis is that it will tell you where the two systems together will remain stable if there is a fault happening in the system. So in the last graph, you can see that there is this particular region that both of them will still remain stable. And if a fault occurs and if you still stay in that region, the whole system will remain stable. So the analysis that we did, it can very quickly show the boundaries, and it is actually pretty easy to find a margin for such a system, and it doesn't require solving equations or anything like that, and it has potential to go to actually expand it to larger networks. The details of this particular study is also in this second paper that I put here. If you're interested to understand how we have derived all these boundaries and what each of these boundaries is, you can read this paper here with all the analysis in that. Now, we decided that, okay, now we've done a GFLI, GFM system. What if we want to look at a larger system? Can we expand these analysis to a larger system? Well, very difficult, because you've got so many different inverters, so many interactions between them, applying a fault. Yes, obviously you can do EMT analysis and see whether the system remains stable or not, but we wanted to see whether we can get any indication of stability when we've got a larger system. Now, what could be an indication? When you look at a very simple system, a single IBR system, you've got this SEP, a stable equilibrium point, and UEP, unstable. You know that if you actually go beyond UEP, your system becomes unstable. When you're at the SEP, you are in the normal operation. Now, the distance between the 2 points kind of give you like some sort of margin. The larger the distance between your SEP and UEP is, the larger the chance of remaining stable. Obviously, it depends on what controller you're using. Obviously, it depends on like so many other things, on the fault itself. But the larger the distance between SEP and UEP, the larger the chance of stability. So we actually tried to get inspired by that and try to look into like coming up with a margin that can help us. This is when you look at the two IBR system that I just introduced earlier, similar thing happens. You know, when the distance between the two in that three-dimensional graph is larger, it means that the margin for stability is larger. So we've been working on a methodology in the last 6 months or last 12 months, I can say, to expand what we've done here to a larger system, and we've been successful to apply that methodology to a system where it's a radial system. You've got any number of grid forming or grid following inverters in that. It will solve some differential equations for you in the background in an iterative way, and it will tell you this margin. It will tell you that, okay, in this large system that you've got, for example, let's say you've got 20 IBRs in that, again, for the moment, what we have is a radial network. In that radial network, that you've got, let's say, 20 IBRs, some of them are grid forming, some are grid following, and you know the impedances in between them, it will tell you that distance of this system, the distance between SEP and its UEP. Now, you might want to change certain things in that system, and then you'll see what is happening to your distance. So it can essentially help you to plan a system. One very interesting application, for example, for us in Australia, would be renewable energy zones. We are building some renewable energy zones, and now we are in the design phase of those renewable energy zones. If you've got this tool, as soon as we, for example, let's say this is available to AEMO, so they can look at this and see, for example, in this particular renewable energy zone, if we place inverters in these different areas, this is the margin we get. Now, if we change something, or if I add a grid forming inverter in another place, the margin might be larger. So they can use it and plan the system that way. So we are trying to finalize that very soon. Hopefully, it will be a publicly available tool, and we can make it available. I think I'm out of time. Very quickly, I'll talk about the two enhancing controllers that we've got. So based on the analysis that I showed for transient stability, and that the voltage loop might become unstable, very simple fix is that instead of having you know, the limits of your reactive current between negative Imax and Imax, simply put it between negative Imax and 0, because you wouldn't need that, and it can only make your system unstable. It wouldn't help. So that simple fix can help with that endpoint thing that I said, and this is one test we did, and it helped. The other fix or the other enhancing controller is this simple APRC, Adaptive Power Reference Control. When you're subjected to a fault, if you add this very you know, simple blocks here, and the details of them are in the second paper that I introduced in this presentation. Essentially, it is equivalent to putting a gain, an adaptive gain, and it can be only activated when you've got a fault. It will help you to recover even if there is no SEP in the system. Essentially, it will drop the power reference while you go through the fault, and it can very easily recover from the fault. It will essentially, and particularly if you only put it when you have voltage sag, it will not interfere with other controllers that you've got in the system. This is one scenario. Without APRC, we had an unstable system, and with APRC, we could very easily recover and go back to normal operation after the fault. This is another test scenario when we had a line tripping. So to summarize, very briefly, I introduced the work we've done on transient stability of grid forming inverters, and we saw that current limiters can negatively impact transient stability. And if you've got a Q-prioritized current limited GFMI, you might have an unstable voltage loop as well. And based on the analysis that we had, we saw that this can be applied to single GFMI, multiple multiple IBR systems in general. And based on these analyses, we had a number of enhancing controllers. Thank you so much for your attention.